Hi kids, so Mrs. Geiger here. So I'm going to take a look at this cartoon and we're going to analyze what's going on. My question for you is, if you've ever been to the beach and you see that the sun is relatively the same distance from the sand as it is from the water. But have you ever experienced this, where you get out of your chair or off your blanket, you step on the sand and, ooh, that is hot. And you have to go as fast as you can, ooh, to the water, where the water feels much cooler. So the question is, if the sun is pretty much the same distance from the sand as it is from the water, why is the temperature of the water so much lower than the temperature of the sand? All right, so hopefully you had some time to think, and we know that the sand and the water absorbed the same amount of heat, but their change in temperature was different. And this is due to a factor that is called the specific heat capacity. So you're going to write this down with me. So capacity tells us how much heat something can hold, its ability to hold on to heat. So specific means that each material will have a different amount, and the specific heat capacity is defined as the amount of energy needed to raise. So we're going to be raising the temperature, but we're going to be raising a certain amount of the substance. So we're going to say 1 gram, right? That's the mass of a substance by 1 degree Celsius, or 1 Kelvin. 1 degree Celsius is equivalent to 1 Kelvin. So if you raise the temperature of a substance by 5 degrees Celsius, you've raised it by 5 kelvins. It's the same difference. All right. So we're going to talk about units, and we're going to talk about how we write this. The symbol for specific heat capacity is C, and that's for capacity. And the units for specific heat capacity are joules per gram Kelvin, or joules per gram degrees Celsius. So it's the amount of heat that it takes to raise the temperature of a substance by 1 degree Celsius, and they're all calibrated to be per 1 gram. So the one that you really need to know about is water. This amount is 4.18 joules per gram Kelvin, and that is on your reference tables on table B. And we are going to be able to use this amount in order to do calculations moving forward. Very often we do a reaction near water, where we surround it by water, because we know that if a substance gives off heat and water, it's surrounded by water, water will absorb that heat. So we can put, let's say, an amount of water in a container and drop in a substance. And if this is exothermic, it's going to give off heat. So the amount of heat that is given off by the object will be equal to the amount of heat that is absorbed by the water. And that's the law of conservation of energy. So when we do that, we can measure how much heat is being given off. Now, sand versus water, let's go back up to our example here. Water has a particularly high specific heat capacity. So what that means is that it takes a lot of energy to change the temperature of water compared to the amount of energy, the amount of heat that it takes to change the temperature of the sand. But this also means that water will hold on to its heat more than sand will. So if you've ever gone to the beach in the evening or at night, you might notice that the sand is cool, but the water remains warm. So even though it takes more energy to change the temperature, it also holds on to that heat more, and that's why we say that water has a very high specific heat capacity. All right, let me move my screen over. So what we're going to do next is we're going to talk about the difference between heat and temperature. Even though it seems like they're interchangeable terms, they're really not. So heat we can define as all of the thermal energy of a substance and this is due to the motion of the particles. Now, how is temperature different than that? Temperature is just part of heat. You'll remember that when we talked about our heating curve, right? Heat was being added throughout the whole process. So time or heat is being added throughout this whole process, but the temperature doesn't change when there's a phase change. So heat has the symbol of Q, and heat is equal to the kinetic energy plus the potential energy of a substance. So when we're looking at how heat changes, we need to think to ourselves, is this a kinetic energy change where the temperature is changing? Or is this a potential energy change where the position of the particles is changing? All right, so now we're going to go ahead and define temperature. Oh, I'm sorry, let's put this here first. Heat has the symbol of Q. I have all these stream marks. And the unit for heat is a joule. And joule has the abbreviation of a J. All right, so how is that different from temperature? Temperature is a measurement of the average kinetic energy of a substance. So, while heat is the kinetic energy plus the potential energy, temperature is just the kinetic energy. And this is due to the speed of the particles. All right, so while heat is measuring all of the energy, temperature is just measuring how fast they're moving. All right, so you need to know that we measure temperature in two different ways. Temperature has the symbol of T, capital T for temperature, and its units are degrees Celsius, which we have the symbol of degrees Celsius like this, or Kelvin, and Kelvin gets a capital K as its unit. All right, so that's the difference between heat and temperature. So when we go back to this picture, both the sand and the water absorb the same amount of heat, but the temperature change is different for the water than it is for the sand. So we're going to talk about this process called calorimetry. Calorimetry is a lab technique where a sample is placed in or near water in order to determine the amount of heat that is absorbed or released. We're going to use one of the heat equations from Table T in order to solve problems that have to do with calorimetry. Whenever you have calorimetry, you're always going to have a change in temperature. All right, so we're always going to have a change in temperature whenever we have a calorimetry problem. And we're going to use the equation Q is equal to the mass of the substance times its specific heat capacity times its change in temperature in order to determine the amount of heat. So let's go ahead and define these terms. Q is the heat, and it is going to have the unit of joules. M stands for mass, and M is going to be in grams always. C, remember, stands for specific heat capacity, and it is going to have the unit of joules per gram, degrees Kelvin, and delta T stands for change in temperature. Now, what is this triangle-looking symbol here? That's actually a delta. So this symbol is the Greek D, and it's pronounced delta. And that's because if you think about like a D, like how we draw it, and then it kind of fell over, that is the Greek D. So that stands for that there is a difference and that's where we get the term from. So when you have a difference, what does that mean mathematically? What do you think you're going to have to do? That's right. So the change in temperature is always going to be defined as the T final minus the T initial. What did you start, or what did you end at, minus what did you start at? So that's why we use the delta symbol to talk about the difference. So if you ever need the final temperature or the initial temperature, don't forget that this delta T is actually T final minus T initial. All right, so that covers if there is a temperature change, but what about if there's a phase change? All right, so just like how we have our specific heat capacities, the amount of energy needed in order to change the temperature by 1 degree Celsius. So heat of fusion is going to have to do with melting and freezing. So heat of fusion, remember that fusion has to do with melting and freezing. So instead of saying like specific heat capacity is the amount of energy needed to raise the temperature, when something is melting, it's not changing its temperature. So we don't need to worry about what that temperature term is, but instead heat of fusion is defined as the amount of heat needed to melt 1 gram of a substance. So when I see the amount of heat needed to melt 1 gram of a substance, we're assuming that that would be an endothermic process. But we can also say, or the amount of heat given off when 1 gram of a substance freezes. So heat of fusion has the symbol H sub F, and it has a unit of joules per gram. So it's how many joules of energy it takes to melt 1 gram of the substance. Heat of fusion for water is equal to 334 joules per gram. So what that means is that if you had an ice cube that weighed 1 gram, it would take 334 joules to melt that. If you had an ice cube that weighed 2 grams, it would take twice that amount to melt that ice cube. Twice as much heat for twice as much mass. All right, next, heat of vaporization. I think you got it, what this is. So heat of vaporization is used for, did I put freeze melt? Yeah. So this would be boil or condense. And same thing, instead of the amount of heat needed to melt 1 gram, this would be the amount of heat needed to vaporize or condense, and I'm going to switch, say needed / released to vaporize or condense, right? So if the energy is being absorbed, it's vaporizing. If the energy is being released, it is condensing. One gram of a substance. At standard pressure. All right. All right, so HV, so heat of vaporization has the abbreviation HV, and its unit is the same as HF. It's going to be joules per gram. All right. And for water, it's going to be equal to 2,260 joules per gram. So if you had 1 gram of water, it would take 2,260 joules in order to vaporize that 1 gram. And if you had 2 grams, it would take twice